Hello. Welcome to the final presentation of today. It's a presentation from Epic Games, from Wouter, about scaling large worlds in Unreal Engine. Bear in mind, this is the last presentation for today. After the presentation ends, please leave swiftly and with all your trash. Also, keep in mind that tomorrow's presentation is the Baldur's Gate presentation. It starts at 9, so be here on time. And then I'm going to hand it to Wouter.
All right. Can you all hear me fine? All right. I'm sure you're all very eager to get dinner after this, so thank you for sticking around. So today I'll be talking about large worlds, but specifically actually numerical precision. So yeah. Very exciting, right? Let's start out with a demo, right? So what I'll show in a minute is a first-person shooter. Well, not a full one, as you'll see, in a large world set in UE4. So I'll be showing the same content at the origin, but I've also moved it to 21 kilometers from the origin, and then to 1,000 kilometers from the origin. And so let's take a look at what that looks like in Unreal Engine 4. There we go. So on the left at the origin, on the right at 21 kilometers. And so already you can see that there's some kind of jittering happening in the gun animation. And then when we get close to the wall, we can see that the material on the back wall, which is doing world space texturing, is suffering from some kind of aliasing or resolution problem. Right, so the expansion of the world size clearly introduced a bunch of problems. This can show up as jittering, flickering, low resolution, but you can actually also see things disappearing. So actually, I just forgot that I didn't show the 1,000-kilometer one. I don't need to show you because basically you can't see anything. Everything just disappears. So there you go. What is causing this problem? Well, we used to represent all of our positions with regular floats, so 32-bit floats, or float 32. As a quick recap, the float32 format is comprised of 1 sign bit, 8 exponent bits, and 23 mantissa bits. And the mantissa bits sort of define the precision that you get. And you actually have 1 implicit bit of precision. So you get really a total of 24 bits of precision here, which is just not enough if you want to build very large-scale worlds. So in the Unreal Engine, positions are represented in centimeters. And so let's say, for example, we have a mesh at 2 to the power of 23 centimeters, which is roughly 84 kilometers out. Then we can take a look at the bit pattern that goes along with this coordinate, which I've shown here on the right. And so if we then set the smallest bit that we can set in the mantissa, then we get an increment of 1 centimeter. So any smaller increment will get rounded. The minimum precision we get here is really just 1 centimeter. So 1 centimeter is not enough precision. We will get jittering. But meanwhile, 84 kilometers is actually not that far out. So we need some kind of solution here. So UE4 set the maximum world size at 20 kilometers. And this is a calculation that you can do either way. But if you set a minimum precision that you would like, then you can kind of work backwards from that to see what the maximum world size should be. And so in this case, you arrive at about 1/16 of a centimeter precision at the edge of the world, so in the worst case. So in UE5, we need larger worlds. Why? Well, first of all, we're trying to build games that are larger, that are streaming. And so previously, we might have built games where you just load a different level. but with streaming games that is supposed to be seamless, right? So that no longer really works. But more importantly, actually, we also ship our engine to a bunch of licensees that are building, for example, simulators. And so we have specific licensees that are doing flight simulators, and those are then, for example, planet scale environments. And well, flying around a plane in 20 kilometers is going to get boring pretty quickly. So we want to expand the world size. Also worth noting that, so I've put on the slide here, is 1/16 precision enough? Well, I'll give you a spoiler, it's actually insufficient. It's not enough, because as you perform more math operations, the error will actually compound. So if you start out with 1/16 precision, you might end up with something that looks terrible. So even small errors can actually become quite visible in the right conditions. And anecdotally, we've seen precision issues at offsets that are as small as 5 kilometers. So the natural question that you might ask is, okay, so should we just find replace all floats with doubles? And well, on CPU, sort of, but not really. So we do use doubles on the CPU, but this is also not trivial because, of course, there is a performance impact on the hot path. You will use slower operations. You might have increased memory usage or increased memory bandwidth that you see. Also, there's a variety of algorithms that might just not scale to this sort of thing. For example, if you have an octree that spans your entire world size, and then suddenly you change the maximum world size from floats to doubles, then suddenly your octree might gain like more than 20 extra levels. So you also need to be mindful of these sort of things when you refactor your code. And then also, yeah, brings us to the last CPU point, which is that the Unreal Engine is fairly big. There's a lot of code in there. I'm sure your engines are also going to have quite a bit of work if you try to just replace the data type that you're using everywhere. But actually, CPU is not the thing that I'm here to talk about. I mean, this is about graphics, right? So I want to talk about the GPU. And there the conclusion is really no. We don't really want to use doubles on the GPU because the performance is just not there. It's just not very good. So there's the obvious things, such as you will have double the register count, which impacts occupancy. So we need to be careful with that because that might just crash the performance already right there. But then both on AMD and AMD, both on NVIDIA and AMD, you very likely will see bad performance just out of the instructions themselves. So it's not uncommon to see things like 1/64 rate for just simple math operations. And then type conversion is also quite expensive. And this is, in my opinion, unlikely to improve as GPU hardware vendors are more likely to accommodate machine learning and AI usages, which are trending more towards int8 or int4, so not the other side of the spectrum, like doubling the data. So very quickly, this is a snippet from the CUDA documentation, and here you can actually interestingly see that if you buy one of their nice enterprise GPUs, that your 64-bit performance is actually quite a bit better. But unfortunately, we cannot rely on all of our customers to just buy H100s or whatever to put in their PCs. So we can't use doubles, but then the next question that you might ask is, so why do we store these huge values at all? Why do we need to store these incredibly large offsets from the world origin if we're just trying to render this small tile around the player where the player is actually located, right? So in theory, we could just translate everything on the CPU, ship that data to the GPU, and then render it. So really, we work with a kind of translated world where the world is shifting rather than the player. Yeah, so that's the first idea. It's actually a pretty good idea. So we call this like translated world space, but you can also call it camera relative world space. In terms of precision, this is really good because the characteristics are such that the precision, absolute precision, goes down as the vectors get larger. And because things are camera relative, you get the smallest vectors near the camera, and therefore you get very good precision where you need it. And in terms of performance, well, we just use floats like we did before, so that's pretty good. So is the problem solved? No, it is not. That would be a very quick dinner that you could have had right there, but you're not done yet. So the major problem with this is just that if you make things camera relative, then literally everything moves when the player moves. So like any modern renderer, you don't actually upload everything to the GPU every frame. You keep objects in a buffer on the GPU, and then you do a sort of indirect draw. But so if things are camera relative, then you will need to update all of these objects every frame. And that is just too expensive. This doesn't just affect things like objects to render, but also several GPU compute structures, such as instance culling grids or world space GI caches and stuff like that. If that wasn't convincing enough yet, then there's also the problem of how you handle multi-camera, so things like split screen or render targets. So it's not really even a per frame thing, it becomes a per camera per frame thing, which is, yeah, sort of an intractable problem once you try to scale up the number of objects. And then lastly, we have a bunch of existing content, specifically materials, that we have to support and keep supporting, and those explicitly rely on having some form of absolute world position available to do calculations with, and these calculations are user specified. So we definitely need some form of absolute world position, so we need a high precision vector format on GPU. So what are our other options here? Okay, ID number 2. So if we were happy with the world in Unreal Engine 4, but it's just too small, so why don't we just tile it, right? We can take that world and we just repeat it in a sort of tiling fashion. So we take, if we have a point in the world P, then we take that original coordinate and we'll rename that to be called offset, and then we add an extra value, an extra float to that, which we call the index value, or we call it tile. And then as that point moves across the world and crosses the boundary of where the world edge used to be, we just increment the tile value and reset the offset such that you kind of get this repeating pattern. Yeah, a pretty simple solution, right? So if we then represent points as a tuple of tile and offset, then how do we actually perform math with this, right? Because then we have to start plugging this into shaders and materials that perform math with this. So the naive way to do this is just element-wise. So if we have 2 coordinates with a tile and an offset, we just sum of the tiles, sum of the offsets, and we're done. Similar with multiplication, and for stuff like transforms, it's simple because we actually don't really care about having very high precision rotation or scaling. So we just keep those in a regular 3x3 transform in single precision, and then separately store and apply a double precision translation vector. And then for transforming directional vectors, we can just skip that translation altogether. So let's take a quick look at performance. So we do have 2 times the number of math instructions if we try to do this, but that's a lot better than 64 times the instructions, right? And also, it is really only applies to whatever we do in double precision. We do have an increased memory cost in VRAM and registers, especially registers, really, which is going to potentially affect the occupancy. We can actually optimize memory usage quite a bit by sharing the tile value across multiple different points if we know that they lie close together. So for example, if we have a particle system, then we can be pretty certain that all the particles are going to be somewhat close together, and so we can upload one tile value and then sort of implicitly share that tile value across all of the various offsets that we upload for the specific individual particles. So overall, this is certainly more expensive than camera relative world space, but this is definitely also orders of magnitude cheaper than using doubles. And this system is actually what we shipped in Unreal Engine 5.0. So let's take a quick look at a second demo. Okay, so here I have Unreal Engine 5.0. On the left at 21 kilometers, on the right at 1,000 kilometers. And so, hooray, the right-hand side actually shows something right now. So it's no longer a black screen with objects that are just completely broken. Things are actually looking quite fine. Great. There's one problem, which is that if I actually play this, we still see jittering in this animation. And if the character moves closer, and we take a closer look at this, it's maybe a little bit hard to see from the back there, but if you're good at pixel peeping, you'll see that the material in the back still is showing a slight form of aliasing in the sampling. So yeah, the world is expanded, but we still see precision issues. So the styling strategy has some issues. So what is happening here? So I lied to you earlier, unfortunately, because the math operations that I described as element-wise, that's kind of nonsense if you think about it. Because, so for example, here I have a vector p, and then in the middle I scale that vector, I just multiply it by 0.5. And it's clearly still in tile 1, 1. However, the coordinate now reports that it is on tile 0.5, 0.5. So yeah, that clearly doesn't really work if you try to generalize this. Similarly, if you just add a delta vector to this point, then well, you can actually cross the threshold of the tile without changing the tile value, which is especially problematic because we kind of defined the tile size as the maximum coordinate that you could have without crossing our threshold of precision. So by sort of overflowing this, we are potentially losing precision, yeah, just through calculations. So you can do sort of a regularization step, right? You could imagine, for example, for the right-hand side, you could just do kind of a modulo operation and then work with that to determine the right tile again. But that doesn't really stop the precision loss from occurring in the first place. And also, really, that means you now have additional performance overhead, or you need to rely on users then somehow manually calling these regularized functions, which is just confusing API as well. Right, yeah. So another problem is that we kind of, so far in this presentation, assumed that 1/16 precision was sufficient, but at the edge it's not. So specifically with materials that simulate wind with vertex animation, we saw precision issues that are a lot closer. One option that you might consider is, can we just string the tiles? So perhaps if we just cut off the bad parts at the edge, the system works well enough. But that actually also, if you think about it, works against what I said prior about those particle systems. So if you are implicitly assuming that the particles are close together and therefore share as a single tile coordinate, then if you start shrinking the tiles, then that assumption starts kind of breaking down or becoming less likely. And so you might have spots in your runtime where at some point you suddenly just have to update a bunch of points because they moved just across the boundary of a tile, which then could cause frame time spikes. So not great, right? Not great. So yeah, also reducing the tile size does improve the worst case precision, but if we want to add 1 bit of extra precision, we actually need to halve the tile size, right? So on here, I've drawn out a single tile, and if we want to get rid of the worst level of precision, the dark red zone, then we need to cut all of that off, which is half the tile size. And so if we want to gain 2 bits, we need to cut off significantly more. And so in general, if we want any substantial precision improvement, we will end up cutting away a lot of the space we gained. Another annoying property that we saw is that your precision actually starts ramping up and down per tile. So the value of the offset field of a point shrinks, grows and shrinks as you move across the tiles. And then precision will also grow and shrink along with that value. And so you end up with these islands of good precision amongst the sea of imprecision, really. And this is pretty unintuitive for users, because what happens is they end up building content, and then they perhaps test it at like 1 million kilometers out, and then it works great there, but then they move it to only 20 kilometers, and then it breaks down. And then, yeah, that's hard to figure out why you then start seeing these problems. And also conceptually, having these islands of precision is kind of worthless if you have to cross a sea of imprecision to get there. So we would much rather have like a system that kind of follows the semantics of regular floating point and gives us a nice contiguous zone with precision in the middle. So shrinking tiles is not a great solution overall, and if we zoom out, we doubled the bit count, but we only gain a very little space, and we have these weird semantics. So tiling is not that great of a solution. So can we do any better? Could we perhaps just use all of the bits instead of trying to have this separate tile and offset value? So this brings us to the third format, which is called double float. Why is it called double float? Well, my talent is not in naming things. That is much is obvious. I'll also abbreviate it to DF. Similar to the last format, it also uses a pair of floats, but instead of a tile and an offset, we will store a high and a low float. And so if we take a double precision value, the idea is that we store as much of its precision as possible in the high float, and in that process we will incur rounding error, and so we take that rounding error and we just put it in the low float. And so if we know the rounded value and the error, we can recombine those to the high precision value. So this format has been described in literature for a long time. I found a paper as far back as the 1970s, and that's because it was, or still is, popular in scientific computing, not only for double precision, but also for example, quad precision if you're doing theoretical physics or something, I don't know. And there's a large body of these papers which describe a lot of the different operators, so that's quite nice. And there's even quite a nice paper here that I've listed at the end, which gives a listing of several of these operators with a theoretical and a measured error bound, so you get kind of a more rigorous foundation with this technique. So how does this compare to just the regular 32-bit floating points or doubles? So we get 48 bits of precision, which is less than you get with float 64, which has 53. But overall, that's not too bad. That's probably enough for what we want. We do end up with 16 bits of exponent. That's sort of unavoidable. And it's important to note with that it doesn't actually extend the range of the exponent, of course, because, well, it's just supporting two separate floats. But that's okay, because we don't really need to expand the exponent anyway. We are okay with that range. We just want more precision. Okay, so how do we perform math with this? So most operations in this structure follow the following. Most operations with this data format follow the following structure. So first you just perform the operation. So on the right here, I have a sum operator, and at the top we just do the sum. You do left-hand side plus right-hand side. And so after you do the operation, you actually revert it. You calculate you apply the inverse operator, and then from that you calculate the error that was incurred when you performed the operation. And so once again, if you have the result of the operation and the error that was produced, then altogether you get the more precise result. So on the right, yes, we perform the sum, we undo the sum again, measure the error, and then return that as a df scalar. Yeah, so performance. If we take this example, so this same operator, this is quite a simple operator if you think about it, because we're just taking two single precision floats and summing those up to a high precision df scalar. This is already 6 instructions, which, again, better than using float 64, but quite expensive. And if we take a look at an operator that actually sums up two df scalars, so two high precision values to take the sum of that, then we end up with 20 instructions. Still better than the float 64, but too expensive. We want something cheaper because we're going to use this a lot. Fortunately, there is a cheaper shortcut that will take, but I'll talk more about that later. In terms of memory usage, it's not as easy as the previous format. So we can't really use that trick with the tile index because, like with floating point, everything shifts around. So you can't really rely on any particular part being constant. But you can actually store points as relative values compared to a reference point that is nearby. And then keep both of those as single precision and then recombine it in the shader. I'll talk more about that later, but this is like particularly useful for instances. But yeah, generally the conclusion there is it's quite expensive. Yes, so a note on fast math. So shaders are usually compiled with the fast math option enabled in the shader compiler, which means that the compiler ignores several aspects of the IEEE floating point standard in order to make things run faster. And so in particular, it allows the compiler to perform reassociation and contraction. And reassociation here means that the compiler may reorder operations. For example, in this example here, the compiler can decide to perform the subtraction before the addition, which means that a minus 8 then can cancel out to 0, and then the compiler finds out that there's 2 operations that were saved. Hooray, good for performance. But this also is nonsense because we're working with not infinite precision theoretical math, but with floating point numbers which have finite precision. So after each operation that is performed, after you do the sum or the subtraction, there's actually an implicit rounding step that is performed in the actual hardware. And so if you just start reordering things, the results actually do change. So if we take a look at that operator that I highlighted before, and we perform the reassociation optimizations, you can work this out step by step. But what you end up with is that the error calculation just ends up being 0 statically, always. So we just lose all of the extra precision that we just gained. We just end up with a 32-bit float result. In other words, the algorithm breaks. Contraction. Contraction refers to fusing multiple instructions into one or vice versa. So for example, here we have addition and then multiplication, which can be combined into a single fused multiplication and addition operator. But these fused operators typically have different precision semantics than the separate operations. And again, some of the functions for double floats will break if contraction is allowed. So that leads us to the conclusion that fast math must be disabled, but while most shader compilers do offer an option to disable fast math globally, we don't want to do that because fast math is quite important for performance. And so we really only want to turn it off in these specific sections, these specific functions, where we want to make sure that these are kept intact, and then everything else can be left to be optimized. So how do we do that? So HLSL and GLSL, they have the precise modifier for some time now, which does very effectively stop fast math. So in this example, the calculation of func B will not get fast math optimizations. Unfortunately, there is somewhat perhaps unexpected side effect, which is that it also blocks the optimization of all the dependencies. So the precise modifier really spreads upward. So really, the calculation of func A, for example, will also not get optimized, which, well, it's technically correct, but it's too much. We might be missing out on potential optimizations here. Also worth noting that with the precise modifier, the semantics are not always well defined. So for example, DXC now has support for modules, but when you have a precise modifier and then you include that in a function that you are exporting from a module, and then you use that function elsewhere, that spreading semantic that I talked about earlier might not work as you might expect it to. There is a proposal to fix this in HLSL, which I've linked to here, by introducing an alternative scope-based math mode, which really makes more sense and would be a perfect fit for this application right here. So, I mean, if you are interested in this, you can always give it like a thumbs up or something to motivate Microsoft, you know, that always helps. If you're working with specific devices such as consoles, you might have other options. So some AMD-based platforms do offer access to RDNA intrinsics, which then just map directly to the instructions without performing optimizations. For example, here the v-add F32. And even if your specific favorite platform doesn't have this, it might have a fused multiply add intrinsic, which also doesn't get optimizations, and then you might be able to reconstruct whatever else you need with that particular FMA intrinsic. Very briefly about Metal. So the Metal manual specifies 2 possible pragmas for configuring fast math. Unfortunately, my experience with the version I tested, these don't really work as I would expect them to. So setting math mode to safe doesn't actually prevent reassociation. But I tried the bottom 2 Clang pragmas, and they work perfectly as expected. There is also the Metal shader converter, which I believe goes directly from DXIL to Metal IR, but I've not tried this yet. So the Unreal Engine targets Falcon, OpenGL, SM5, HLSL, and more. And it does so through cross-compilation from HLSL using SPIR-V. And well, the good news there is that SPIR-V has very good support for disabling fast math on a per statement level with the no contraction decoration, which somewhat confusingly also prevents reassociation. So it's more of a no fast math decoration. So the support is really already there at a low level. This is more of an issue with shading languages, as far as I can tell. So now we have 3 different formats, and each of them has advantages and disadvantages. And then the question naturally becomes, how do you put all of this together in the Unreal Engine to make it into something coherent? And this really is the bulk of the work, just refactoring everything, every single shader that deals with any sort of position, and making it work correctly with one of these formats. The general strategy that we used, that was quite successful, is to use translated world space whenever possible, and then when caching or absolute world space really is required, then we use double float. So I'll demonstrate that in a minute with the example of drawing meshes, but this strategy really has worked for a variety of systems that I've looked at, such as nanite and vertex factories, but also more general representations of the scene on GPU, so like geometry and lights, both for reading and writing, for primitives and instances on mobile and on desktop. It also has worked for distance fields, for instance calling. In virtual shadow maps, we have a clip map structure that is in world space, also was able to apply it there. And then Lumen is still a little bit of a work in progress, but the radiance cache with the probes clip map, mesh cards, and so several forms of tracing all can be adapted to this as well. So yeah, I promised you an example, and here it is. So it's not super complicated, really. First, we just upload the vertices, the object transform, and the camera transform as usual. And we, the vertices just remain in single precision, and it's just the mesh position and the camera position that we upload as double float vectors. And then also, again, the mesh rotation and scale remain as a single precision 3x3 matrix. So on the GPU, we can then perform a single double float subtract operation, which subtracts the object from the camera position. And so we get this relative vector from the camera to the object. And we know that this resulting vector will be small because the object is close to the camera, otherwise we wouldn't be rendering it in the first place. So after the subtraction, we can just bring that result down to single precision, and then perform all the remaining steps in single precision. So we really only need one subtraction operation here. And then the next frame, we can just keep all that mesh data cached, and we only need to re-upload a new camera position. And so when we are dealing with instanced geometry, like foliage, we can optimize the memory usage and bandwidth more. And so instead of storing a df vector for each instance, we can store one df vector as a root point for all of the instances, and then make all of the instances relative to this root point, store that as single precision. And then if we choose that root position appropriately, we can recombine this to a full double precision position on the GPU using only 3 extra instructions. So that's not too bad for the memory savings that we're getting. Right. One more demo. So this is again at 1,000 kilometers. And finally, the jittering is gone. That's a welcome sight. And so if we go close to the wall, then also we no longer see that aliasing that we saw there before. So the most used operation here is subtraction. So as I showed, we use that to go from absolute world position to camera relative position. So it's important for this operation to be as fast as possible. And subtraction is typically performed as shown here on the right. So again, it's basically the addition operator I showed before, but you just negate the right-hand side, right? And this algorithm is very precise, but 20 instructions is too much. It's too expensive, but we can do better. Very easy optimization is just realize that we only need a single precision result, and so we can get rid of some instructions at the end that are really only meant to make sure that the return value has the correct format, that it again fits in the double float format. But that only gets rid of 2 instructions. So we need something more radical. So the question that I would like to propose is, why don't we just do this the dumb way? So we have a high float, we have a pair of low floats. What if we just subtract these pairwise, add the result together, 3 operations, and we're done. That sounds a lot better, right? But does it work correctly? Generally, no. Yeah, so the graph here on the right shows the absolute error that you're getting from performing a subtraction of 2 coordinates with this operator. And so if you're able to read the graph, then you will see that you can get errors on the order of like 2 to the power of 25 if you scale up your input and input coordinates to great sizes. However, there is an interesting line here in the middle, running right through the middle of this graph. And as it turns out, we are lucky because we really don't care about the general case of all these points that are lying to the top left and bottom right. Because really, we care about all the points that are around the camera. And well, that's exactly where that line lies. So as it turns out, this line covers really most of the rendering purposes that we care about. So to make things a little bit more concrete, in Unreal Engine 5, we set the world size to 2 to the power of 43, or about 88 million kilometers. And if your 2 points lie within that range from the origin, so less than 88 million kilometers, and they are within 10 kilometers of each other, then using this operator will result in an error that is less than 1/16 centimeter. So if you're past 10 kilometers, your error might be greater, but I think you'll have a hard time seeing that kind of error at 10 kilometers distance. Because that actually, again, has a nice pattern here, which is that the precision decreases with distance. So the best precision is, again, found near the camera, where you're most likely to notice errors, and then as you increase the distance, the error increases, but you're less likely to notice it. So for most use cases, we can really just perform subtraction with 3 instructions, or 3 operations, which is a lot more palatable. Yeah, as a matter of just kind of demonstrating, I've taken the city sample demo that we made a while ago, and just moved it 380,000 kilometers away from the origin, which, according to Google, is the surface of the moon, but I've never measured it myself, so you'll have to take my word for it. And so whether we're looking at the scene from far away or we're looking at things quite zoomed in, geometry just shows up stably, works as expected without jittering. Now, if you're going to try this for yourself, it's worth noting that certain systems such as Lumen are not fully compatible yet. So you might see some flickering in GI there. There's also an interesting note about materials, which will be the final topic before before I let you get dinner. This is really the last major problems. How do we deal with materials that were altered by artists, by users, not only within Epic, but also by licensees? We really have like years and years of assets out there, and we can't just break all of them. Materials use the absolute world position of the object, the vertex, or the fragment point for many different purposes, such as world space texturing, such as what I did here, vertex displacement math, random seeding, and a bunch of other use cases. So artists typically do write these themselves with a drag and drop material graph editor. So yeah, you kind of just have to deal with it. You can't really step in and refactor this just from a code side. we can't change the assets, but we can change the underlying system under this graph editor so that it produces different shader code for the same material graph, which ends up being a quite nice abstraction because we can just swap out the underlying types without artists actually knowing that it ever happened, ideally. So the natural first thought might be, do we plug double float into this? But that's too expensive. Really, double float is more something that you should use carefully. You should think about what operators you're using and how you are structuring your math. And that is not something that we can really just expect from technical artists to step into every single shader and optimize it for this purpose. So we need something that's a little bit more robust and doesn't have such performance cliffs. And so the compromise we ended up with is that we do still use styling math for user-generated code to avoid this performance impact. And so the fixed function code, so all of the global shaders, but also all of the parts of the materials that are written by the rendering programmers, those all use double float or translated world space, but then specifically the programmable components that artists use, those all use styling math. And so the idea behind this is also well that if users don't actually use absolute world position in their materials, then the systems will all work with perfect precision. Of course, there are plenty of assets that do use absolute world position. So when this material shader code is invoked, we convert the input variables to this styling format on the GPU using the code that I show here on the right. So this is not too much overhead. It's only a couple of operations. But users can also avoid this conversion cost by just using a different space. So a lot of these operations can just be performed in local space or in a translated world space. And then you get not only better performance from avoiding this conversion, but also better precision. And with each engine version, we're making it easier to avoid absolute world spacing materials. And I've included a link here about, with a document that I wrote that kind of goes through several different examples that we found in Fortnite and how you might approach replacing those. So tiling math in materials is a trade-off that gives us both better performance, but also more flexibility and helps to avoid introducing foot guns. There can be occasional precision issues this way, but in reality, it turns out that if you alter your materials in a scalable way, then this really occurs rarely, and it only occurs in materials where users are able to fix the problem themselves. Right, so a couple of closing notes. So the version with the double float released in Unreal Engine 5.4 or Fortnite Chapter 5 Season 2 in production. Unfortunately, I don't have numbers on the conversion from UE4 to UE5 because, well, I didn't work at Epic yet. Now, the introduction of double float with UE 5.4, we measured at the time of introduction was around 0.1 milliseconds of impact on a 30 FPS frame for Fortnite and the city sample demo. But this also varies based on platform and what content you're showing. And after this introduction, there is also a couple of shaders that saw occupancy decrease and therefore needed more tweaking to bring that performance back up. And so there is still quite a bit of optimization that is on the table from the content side, where artists could take the most used materials and kind of optimize it for this more efficient math. And so the majority of UE5 systems today are large world compatible, with some notable exceptions that are still being worked on. But this feature is right now available as an experimental feature in Unreal Engine 5.5, which I think is about to release or has released. So if you want to check it out, you can. And well, finally, I would like to thank the rest of the Epic rendering team, and especially Kevin and Juan. And of course, I would also like to thank the GPC organizers. And finally, I would like to thank you. Thank you.
Okay. We have 10 more minutes, I think, for questions.
Okay.
Yeah, so let's take a few.
Hi, thanks for the talk and nice overview of the techniques. You said before that you're currently using like camera relative world space and then fallback into double floats. Like, how is this both fallback working? Like, is this kind of like user selected, or do you handle this automatically? And if you could actually like share any examples of which like systems cannot work with like camera relative workspace and you actually need this for?
So is the question which systems are able to work with camera relative, or?
So which ones are actually you forced to use the fallback, to double float fallback? Like,
Right.
You know what I mean? Like if like camera relative seems to be kind of like very, like a really good approach for like most things, which things actually don't work with it, and you're forced to use double floats.
Yeah. So the reality is that actually, so far, I've not really encountered any systems where we had to use double float throughout. So usually we can just rebase the math and perform it locally, and the double float data is really just needed to have things be consistent across frames. I know there is some usage in, for example, I think the path tracer, but there it was, I think, also used because it was still sort of experimental code, and so it's easier to prototype if you just do things in high precision and then later optimize it further. Yeah. Yeah, the tiling math, I think, is also still used in Niagara, but that's also because we expose the actual shader code to the user there, so it's also not as easy to swap it out. But otherwise, we pretty much just convert everything to be camera relative after you enter the GPU and have all the data.
Did you ask your question?
Yeah, thank you for tackling this problem. It's annoyed me in quite some games over the years. My question is, if my brain is correct, you have moved 1/6 of the way to fixed point. So hardware support aside, would fixed point solve this problem?
Well, so the tiling thing is kind of fixed point if you think about it. But yeah, you could also think about things like why don't you use integers or something like that, right? The thing is that you don't really gain precision at the origin if you do that. Well, with this you do. So really you gain more by using double float there. But also there is still a conversion cost typically if you convert from integer formats to float, and the rest of your math is still going to be in floats. So yeah, because this is basically built on top of floats, you kind of avoid that additional conversion cost there as well.
Okay. Was there another hand? Ah.
In the context of BVH building, what did you do there? Do you build it relative to the camera every frame?
So I have to admit that I'm not really very much involved with the ray tracing side of things. But as far as I can tell, this system was already performed I think either camera relative or in some kind of more local space.
Yeah, okay.
Okay, I think that was the last question. Thank you very much for your talk.